a year ago now.
Good. Yeah, welcome everyone again to another edition of the UniKORN talks. Before we will start with today's talk, we'll go over our house rules just quickly. So during the talk, it would be great if everyone could mute their mic and turn off the video to save bandwidth for the connection. If you have questions during the talk, please use the chat and put it in the chat, but we'll try to gather them all at the end after the talk. And if you would like to post a question in person at the end of the talk, just use the raise hand feature and we can let you ask the question. Also, the YouTube questions will be fed back into the Zoom chat and we can read them at the end of the talk. So we have a couple of announcements before we get started. There is next week's talk by Antonio Pontin on next Wednesday at 2 p.m. And also another announcement is our lecture series that we have planned in January about coherences in open quantum systems by Ben Stickler. We're really excited about that, and it would be good if everyone who is interested can go to our website or the research seminars profile, where we have links to a registration for the lecture series. Everyone can register on via Eventbrite and get emails to the series. That will be happening in, I think, the second week of January, so starting on 11th January and going for 5 days every day. So today's talk is by Jack Clarke. Jack did his undergraduate and master's at Oxford before he moved for his PhD to Imperial. He's currently doing his PhD in the quantum measurement labs of Michael Wanner, and his research is focused on quantum state preparation and measurements in the context of pulsed optomechanics. So without any further ado, please take the stage, Jack.
Okay, thank you very much. I'll just share my screen now. There we go. Great. Can you all see that? Is that good?
Yes.
Awesome. So yeah, so thanks thanks to the UniKORN team for organizing these seminars, and then also inviting me to share my research with you all today. So the first thing I want to talk about is going to be pulsed optomechanics, because that's going to be the foundation or the building block for the state preparation protocols I'll talk about later. Okay, so what is pulsed optomechanics? Well, let's say we have a pulse of light here, and it's much shorter than the mechanical mode of interest. Well, what's going to happen is it's going to enter the cavity, it's going to give a momentum kick to the mechanics, and while the pulse enters and leaves the cavity, it'll pick up some phase that depends upon the position of that mechanical oscillator. So we can represent that whole interaction with this circuit diagram here. So we have an interaction between light and mechanics and a unitary operation given here, where NL is the number operator associated with the pulse of light, and XM is the dimensionless position operator of this mechanical oscillator. So if it's described by a annihilation operator B, then B plus B dagger over root 2 is XM. And similar, we might have, we might say that the cavity mode is described by a annihilation operator A. Okay. The only thing I guess I haven't mentioned here is this mu, which is the coupling strength of the interaction. And to find what that is, we need to think about the whole dynamics of this system a bit more carefully. And in particular, when we think about light coming in and out of the cavity, we need to think about the cavity having some finite line width, so it can accept light. And then in principle, the mechanical mode will have some intrinsic damping rate as well. However, we're in a regime where we've got a very short pulse of light coming in, and therefore all the optical frequencies involved will be much higher than the frequency that describes the free evolution of the mechanics, this mechanical frequency, and also the damping rate of the mechanical oscillator. So this is the regime of unresolved sideband regime. And in this regime, the dynamics of the system can be modeled with these set of equations, one for the cavity mode, and then one for the position of the mechanics, and one for the momentum of the mechanics. So there's a couple things I haven't defined yet. This G0 is the single photon phonon coupling rate. So that's describing the rate at which the photons in the cavity and the phonons in the mechanical oscillator interact. And then there's also this input field here, A, which is going to describe the input field of light. And so sparing you the gory details, we can go ahead and solve this system of equations over the duration of the pulsed interaction. And what we end up with is we're able to identify what mu is when comparing to the unitary from the previous page. And so this coupling strength goes as G0 on kappa. Now, for certain systems, G0 on kappa can be quite small, much less than 1, say. And in that case, a common approach is to linearize the interaction. And so what we do is we say, okay, this input field has a mean number of photons, n subscript p. I'm going to say that's much, much greater than 1. And so we can write the input field as some mean amplitude, so the square root of the number of these photons, times by some temporal envelope that describes the shape of the pulse, plus some inherent quantum fluctuations on top of that mean amplitude as well. Now, if we're in a regime where when the light travels in and out of the cavity and picks up a optomechanical phase shift, that phase shift is small and the number of photons in the input pulse is much, much greater than 1, then the important part of the interaction looks like this. And so you see we've enhanced the coupling strength to chi, which has this factor of the root of the number of photons, but we've done so at the expense of linearizing the interaction. And by that, I mean, we've taken the number operator of the light, which will be like A dagger A, and we now have something that goes like the amplitude quadrature of the light, XL, which is like A plus A dagger. Okay. And so now we can think about some experimental values. And here I'm about to show you some experiments that work in the unresolved sideband regime. But the protocols which we suggest could be implemented in other experimental systems that are also unresolved sideband. So one point I'll make is that generally speaking, G0, this coupling rate that determines the strength of the interaction, is going to scale as 1 over the square root of the mass of the mechanical oscillator, the thing that's oscillating. And so for more massive systems, mu is going to be small, and for very tiny systems, mu could be greater than 1. And so that's what we see here with these examples. So these two systems on the left now are systems with small mu, which is smaller than 1, and they're silicon nitride or silicon nanobeam type resonators. And these are both on sort of the picogram scale. And so what they'll want to do is they'll say, okay, let's enhance this interaction perhaps by using this linearized approach. And they can approach chi's on the order of 1, say. Whereas for ultra cold atom implementations of optomechanical systems, which may comprise a few thousand atoms in a trap, say in a Bose-Einstein condensate or something like that, then G0 on kappa is already greater than 1. So you can go ahead and make use of this inherent nonlinearity straight away. Okay. So now let's talk about, oops, my PowerPoint has stopped working. That's always great. There we go. It's working, and sorry about that. Okay, so now let's talk about some of the work we've done. So the first paper I'd like to share with you is this work we did on how you can use this nonlinear interaction, e to the I mu n LXM, to grow a Schrodinger cat state of a mechanical oscillator to larger and larger scales. So what's the setup for this? Well, what we have is we have a pulse of light in some quantum state psi, and we're sending that into an interferometer. Now in the top arm, we're going to have this nonlinear interaction, while in the bottom arm, the light's just going to pick up a phase. And then at the output ports, we're going to do photon number counting. And say in this example here, we've counted n photons in the top port and m photons in the bottom. To describe what this diagram does to the mechanics, we can derive the Krauss operator by reading this diagram left to right and then writing down the Krauss operator right to left. And then in the subspace of the mechanics, say this is the mechanical state now, for a particular click event, the mechanics will evolve according to this Krauss map. Okay, so if that input state of light to the interferometer is, say, a single photon state or a coherent state, then we can derive a nice form for what that Krauss operator looks like, where m and m are these number of photons detected. I said it's nice, but it's actually a bit complicated. So let's take an example where, say, m is 1 photon detected, and n is 0, no photons detected in the other port. In that case, our Krauss operator just looks like a simple sum. It's a sum of a displacement operator and then phase times some identity. So this displacement operator is generated by x. So that means it's a momentum kick, and it's a momentum kick of size mu. So this part kicks the mechanical oscillator a distance mu along the momentum axis. So as a cartoon, this is a cartoon of mechanical phase space, where this is the mechanical position and this is the mechanical momentum. So we start off in some initial state of the oscillator. It could be a thermal state or a ground state, say. Then a single application of this Krauss operator leads to a superposition of a copy of the initial state with just the phase term applied, and then a copy of the phase of the initial state that's been kicked along the momentum axis a distance mu. And so we can consider repeated applications, and we'll end up with a state that's comprised of a bunch or many momentum components. And what we aim to do is investigate, okay, how can we choose the phases at each stage to cancel all but the outer two momentum components? And in this way, we've grown the cat state, we've increased the separation. Okay, I've got a cat there as well. Okay, so still thinking about this single photon detection case. Let's go away from cartoons now, and I'm actually plotting the Wigner distribution. So when we're in a regime where mu is large, we can create a true Schrödinger cat state in just one step of this protocol. So we have a large separation here, and we have a proper Schrödinger cat state. But say in the solid state systems where mu is much less than 1, where mu is small, let me define that a bit better. When mu, which will be the separation of these two components, when that is less than the width of the initial state, that's what we're considering on the right-hand side. So the state we get after detecting a single phonon is now much more sensitive to our choice of phase, right? So if we started off in an initial ground state, if the phase chosen was 0, then we end up with the ground state again. So that's not interesting. And the ground state here, we see, we look on this color bar, the Wigner distribution is positive everywhere. It's either 0, which is black, or it's going towards sort of yellow. Whereas if we chose the phase carefully, what we can do in the limit where mu is very small is expand this, and we actually cancel that ground state component. And when phi is pi, we can generate something that looks like a single phonon state. And you see this blue bit indicates some Wigner negativity. So let's get a bit more precise and talk about our scheme. But first I'll shout out the work we were inspired by, which is an experimental work which considered, okay, if you're starting off in some initial thermal state, what does the phase space distribution look like after certain click events or application of Krauss operators? So the 1, 0 is like 1 in one of the photon detectors and 0 in the other. And you see here what they observe is mechanical fringes in the phase space distribution. And so what we're now going to propose is, okay, how can we enhance these features and perhaps grow something that's more non-classical, more macroscopic? So what we're proposing is send in now a train of these pulses. So this top scheme just used one pulse. So use a train of these pulses to realize an application of the Krauss operator many times. And we'll do that every mechanical period. So we're always kicking in the same direction of phase space. And if we herald certain outcomes and choose our phases carefully, we can enhance the separation from mu to n mu. And that'll happen with some probability. So now as an example of what it would look like in phase space, if you choose to grow your cat state over 5 steps, we see that we have this destructive interference on the very last step, where you just have now a superposition of a state at the initial position and a state displaced along the momentum axis, and then there's some interference in between. And the trace of phase corresponds to, for n steps, the nth roots of unity. So here it's the 5th roots of unity. We also think about the open system dynamics. So I said we need to be kicking in the same direction in phase space. So that means we need to model mechanical decoherence in between steps. And also there'll be some detection inefficiencies and outcoupling inefficiencies, which we can model by beam splitters. And so what we're interested now, when we take into account the open system dynamics, is non-classical and macroscopic features of these states. These are the metrics we want to track with step size. So the non-classical features we look at are the minimum of the Wigner distribution and also the total negative volume. So we can quantify how much Wigner negativity we have, which tells us how much we're deviating from a classical probability distribution, which should all be positive in X and P. Whereas the macroscopic features we investigate are quantified by, firstly, this phase space measure by Li and Zhang, which is quantifying the extent to which sharp features extend in phase space. Okay, so we know that you've got, say you've got a cat state, these sharp features are caused by interference, quantum interference. And so this is measuring over X and P the extent of those sharp features. And it's sort of an average over X and P. We also consider a Fisher information-based measure, where now we're quantifying phase space macroscopicity in the same way, but we're maximizing, sorry, overall directions. So this is more of an average, this is more of a picking an optimal direction. Yep. And then these are examples of some of the plots that we get. So the x-axis being the number of steps, M bar here being the initial thermal occupation of the state. We have mu here. And then these n subscript thermals are in fact the number of thermal phonons you are going to add in between steps. So it's related to something like M bar of the environment over Q, be proportional to that factor. Okay, so I should speed up a bit now and talk about the other paper we've got out. And so switching gears a bit, this is on generating entanglement now. So we looked at superposition states. Now we're wanting to investigate entanglement. And in particular, how this linearized pulse-stop mechanical interaction can generate entanglement between two oscillators, say. And we're still working in this unresolved sideband regime, of course, for this interaction to be valid. So let's firstly go over the foundations or the building blocks of these schemes. So we're considering these interactions between light mechanics. So say we start off in an initial state on this side of the diagram, the left-hand side, where the bipartite state of light and mechanics is Gaussian. And by that, I mean it can be described fully and completely by its first and second moments. Then, because this interaction is bilinear in these XL and XM operators, the output bipartite state here will also be Gaussian. And furthermore, we're going to consider measurements on the light field, which are essentially projections onto Gaussian states. And so we're considering homodyne measurements. And in that case, the output state of the mechanics is Gaussian too. So in phase space, what we have, say, for one of the modes, the light or the mechanics, is you have a Gaussian state. It's characterized by its position in phase space, so its mean. And then also this covariance matrix, which will tell you about the width and the shape of that Gaussian state. But generally, we're interested in bipartite systems. So we generalize this picture to two modes. We'll have phase space for each of the modes that are entangled. And then we'll have a vector of means. So we'll have a mean in X, a mean in P for each of the systems. And then our covariance matrix is now 4 by 4. And then we know if we've got a bipartite Gaussian system, we can use the logarithmic negativity as a genuine measure of bipartite entanglement. Okay, so now what we're going to do is go over the entangling stages of the protocol. So firstly, very simply, we have this scheme to generate optical mechanical entanglement, which is just going to be an interaction between a pulse of light and an oscillator that looks like this, that we've discussed a few times now. And then we're going to build on this, use this as a building block to put forward protocols to generate all mechanical entanglement, so entanglement between two oscillators. And we do that in two ways. The first way is an interferometric design. So you have an oscillator in each arm, and then you do homodyne measurements at the output. And then the other design is more linear. It's a non-interferometric design. So you interact with one oscillator first and then the other one later. And what we'll discuss is which of these designs is better for entangling spatially separated mechanical oscillators. And by better, I mean which one generates more entanglement, and importantly, which one allows me to measure more entanglement. So I'll be a bit more specific about that in just a second, by what I mean. But prior to each of these entangling stages, I should say, for each of these oscillators, we also suggest or propose that there's a mechanical precooling step. Now, what is that? What this comprises of is a pulsed interaction with light and mechanics, followed by a phase quadrature measurement on the light. The reason being is that in the Heisenberg picture, this unit tree transforms the phase of the light according to this equation. So what we have is that the phase quadrature of the light has information about the position of the mechanics. And so if we learn about the phase quadrature of the light, we'll narrow the uncertainty in XM in the mechanics. So as a picture and some equations, this is exactly what we see here. So starting off in some thermal state of mechanics, we narrow the uncertainty in a mechanical position. And that way squeezing one of the quadratures. And so we find for the parameters that we're looking at, we only really need one of these precooling steps to really enhance the amount of entanglement we're generating. We don't need to think about cooling or squeezing the other quadrature. Okay, so let's look at a diagram which shows us all three stages. So this is again just for entangling light and mechanics. I'm just showing the light mechanics case because it's a bit less busy. But you have an initial precooling stage, the entangling stage, and then the verification stage. I'll just point out some features of this diagram. So firstly, I want to state that we're considering what happens if you use an optical squeezer after the first entangling interaction. And the reason we're considering using a squeezer is it's been shown theoretically and experimentally that squeezing optical states is a very good way of protecting them from interactions with the environment. So we're saying, okay, we're going to investigate whether it's worth using a squeezer in this setup to protect the amount of entanglement that you're generating. And then this last stage, okay, it's the verification stage. All it is it's just using this interaction again between light and mechanics such that the phase quadrature will pick information about a mechanical quadrature, and if we want to learn about different quadratures other than X, we can wait some time for mechanical position to evolve into another quadrature. So that's what this theta here is. So as a picture, if I was interested in the momentum quadrature, I'd wait a quarter of a period for position to evolve into momentum. So this angle here, theta, is now pi by 2. And in that way, we can repeat this verification, this whole procedure, I should say, many times. And at each stage, we learn something about a certain quadrature, and then we can build up probability histograms and then reconstruct the whole covariance matrix of the state. However, that verification procedure isn't perfect because there will be mechanical interactions with the environment and also optical loss. So in general, the verification procedure is going to underestimate the amount of entanglement that we're actually generating. And let me show you some plots. So I'll explain the top one first. Here we're investigating what the logarithmic negativity looks like as a function of the interaction strength chi and the squeezing parameter r. And so we see that by having a non-zero squeezing parameter, you can sort of extend the region where you're able to observe entanglement. Now, let me explain this bottom plot. So these top two lines here, oh, I should say what the axes are, sorry. This is we're plotting the logarithmic negativity as a function of the interaction strength. And so the top two lines are the logarithmic negativity you generate with the protocol. So there'll always be some optical loss, but we're considering the case where the mechanics hasn't time to freely evolve. And so these two lines are the amount of entanglement generated at time equals 0, say. And the different colors are with and without squeezer, the optimal squeezer. Whereas these dashed lines here are the same thing, but now we've let the mechanics decohere over a quarter of a period. And then these bottom two lines are now, okay, how much entanglement can we actually measure in the verification procedure, given that it's not perfect and there's some loss. Okay, so now let's talk about all the schemes. So here I've just got a plot of the maximum value of the logarithmic negativity our protocols can generate. And it's for the light mechanics and then the two all mechanical schemes. So explaining what's going on, the red color is how much entanglement you generate at the instant of entanglement generation. The little light color on top is basically telling you how much optical squeezing is gonna help you protect the amount of entanglement you generate. And then the blue is, okay, we've let the mechanics decohere over a quarter of a cycle. And then the orange color is we've let the mechanics decohere over a full cycle. And so this was all for a specific value of optical efficiency, but a more detailed analysis will show that for the optical mechanical scheme, you can generate and verify entanglement with very low optical efficiencies. And so you can currently achieve that with present day technology, which is very promising. Whereas now we can compare these two all mechanical entanglement schemes. The first thing to notice is that, okay, there's more entanglement for the non-interferometric design. These little percentage increases on the top of these bars, well, they're smaller for the non-interferometric scheme. So that means that the non-interferometric design, which is just 2 oscillators in a row, that doesn't require as much squeezing, which is good, because optical squeezing can be difficult to implement in this protocol, perhaps. And also, the non-interferometric design requires less ambitious increases in the total optical efficiency compared to this case. And yeah, I guess that's the one of the main results of this work is that the non-interferometric design is better. Okay, so now as a conclusion or an outlook, the first scheme we introduced was using this nonlinear interaction to generate Schrödinger cat states, but certainly this type of work or protocol can be generalized to creating different types of quantum superpositions, perhaps in a 2D phase space now, so not just along one axis. And that could be for sensing or quantum information applications, depending on what the exact state is. And then when we're thinking about generation of mechanical entanglement using this interaction, we've introduced now a protocol that's capable of generating all mechanical entanglement in the pulsed unresolved sideband regime of optomechanics. So in the new regime of optomechanics. And just this week on the archive, together with colleagues from Amsterdam, we have this protocol that builds on this work, and it considers a way to generate and verify entanglement between 2 oscillating modes of the same structure within a mechanical period. And importantly here, we investigate, okay, differing mechanical frequencies of these 2 modes and imprecision in these frequencies, and then also different coupling strengths here between these 2 modes. And so this is really a path towards observing this type of entanglement in the lab, which will be really cool. Okay, so I think that's everything I wanted to share with you all today. So thank you very much for listening. And now I guess I could open the floor to questions if you have any. I'd just like to also thank all the co-authors of the work that I've been sharing today. So thank you.
Thank you very much, Jack, for this very nice talk. Before we start with the questions, I'd like to ask everyone to maybe shortly unmute the microphone and give a round of applause to Jack for this very nice talk.
Basically changing the SRH over respect to the contact.
So thank you. We already have one question in the chat, I think from the YouTube. And that's a question from James Milne. He says, with your cat states, as they grew, they became asymmetric in X and not P ? But after a certain number of kicks, the state became symmetric again. Can you explain this?
Yeah, sure. Let me try and maybe this isn't the most efficient way to do this. Here we go. So yes, thank you for the question. That's really good. So the asymmetry in question is here. Okay. So James is asking on this last step. We see before the final kick, the Wigner distribution is heavily weighted on the sort of the left-hand side, and then finally, destructive interference cancels that. And so the reason why it's weighted on this side is because we chose in our interferometer that this state was conditioned on a particular set of outcomes, 1, 0, 1, 0, 1, 0, 5 times. And so in that case, your upsilon will look something like, there'll be a plus or a minus here, say. So this extra phase here, this plus sign, say, is the cause of this asymmetry. Now, if we had a case where we had 0, 1, 0, 1, 0, 1, so let me, so if we had this instead, maybe this is a bit confusing, 0, 1, 0, 1, 0, 1, then we have a minus sign here. So mathematically, that's where this asymmetry is coming from, this extra phase that depends on the outcome and not the phase chosen here. So I hope that answers your question. I'm sorry if it was a bit, hopefully that answers the question.
Thank you. Actually, I have a question on the same slide. So what would actually happen if you would continue to apply these steps? Would you be able to grow the cat state further, or is there a limit, or what's the limit?
Yeah, that's a very good question. So here, we've chosen this particular set of phases. So what you have here is you have a Krauss operator, a total Krauss operator that's going to be built by a bunch of these individual Krauss operators times together. So we're using an identity that if you choose, say, after 5 steps, these to be the phases at each step, then you'll get cancellation of all but the outer 2 terms. So that's to say that I have to first decide how many steps I want to grow my cat state in. What's the enhancement in mu that I want? And then those will be the phases you pick. If I did an extra step now for n equals 6 and just chose, say, a random phase or even the first 5th root of unity again, say, then I wouldn't get this destructive interference, and I'd be back with a bunch of states potentially without this destructive interference. I mean, the state would be some complicated superposition of many terms along the momentum axis.
Mm-hmm. Thank you. Do we have any other questions? I have another question. At the end, when you were talking about the non-interferometric versus the interferometric protocols, is there a physical intuition or an easy explanation why the non-interferometric performs better?
Yes. So maybe. Yes, I'll try. I'll try and give a physical explanation, and then if I fail, I'll run and show some maths. So basically, if I think about what's the operator that's describing the entanglement, so what's the upsilon here and what's the upsilon here? It turns out that because the way this is structured is that you'll have pieces of this Krauss operator that look like this, D1 and D2. And by this, I mean that this Krauss operator contains displacements which act individually on these modes. Now, in the other case, because of the way it's structured, you will just have a part of the Krauss operator that's a sort of a displacement on a joint mode. So when we have loss and mechanical decoherence, now we're going to see why these two things are separate. So first point to make is that with no loss and with no mechanical decoherence, they're essentially the same protocol, and they'll give you the same amount of entanglement. But when you take into account loss, you're now losing information to the environment through a process where you have individual displacements on the mechanics. So that's going to cause 1, momentum diffusion, and 2, it's going to lead to loss of which path information. So my environment can sort of tell which way this interaction went. Whereas this case, I've protected the light here, and in that when I lose information to the environment now, I'm not losing which path information. I'm still having some momentum diffusion, some dissipation that's going to reduce the entanglement. But in this sort of structure, this loss of entanglement is stronger because of that loss of which path information. So hopefully I explained that okay. Is that? Oh,
yes, yeah. I think I got it. Yeah. Awesome. Thanks. Do we have any other questions from the audience or from the YouTube audience, maybe? I see that we don't have a raise hand. At least I don't have a raise hand down in the Zoom call. So maybe if anyone has a question, just unmute yourself and ask it.
There are no questions from the YouTube chat. Just you.
Okay. So I think if there are no further questions, I ask everyone to thank maybe Jack again with a small clap. And
Markus, I see that there's one raised hand from Sahar.
I think it's a clap, no?
Oh, okay, my bad. Sorry about that, Sahar. That is my bad. It looks like a raised hand.
Yeah, so then thank you everyone for joining our today's edition of the UniKORN seminar. Please come back next week when we have Antonio Pontin speaking in our seminar series at next Wednesday at 2 p.m. And if I can ask you, Jack, to just stay on so we can thank you in person again. Take care, everyone. Bye.
I think I went a bit over.
It's fine. It was perfect.